Yeah, welcome back to my channel, guys. So today we are going to solve the question: find buildings where Alice and Bob can meet, right? So the question has been marked as hard, but yeah, it's a pretty simple one. If we understand what the requirements are, like it's not that bad. If we code it up, we'll see. So firstly, we need to get what the question is asking. So it has been said that there's a heights array which is defining the heights of buildings in the question, and we have been given queries, right? So in the queries, if you see the first query, okay, before moving to that, the question also says that a person can move from one building to other in two conditions only. So the first condition says that it can move from one building to other only in the right direction. So if we say we are standing in an index in building with height 4, so we can only move to the rightwards. Okay, we can move to only these buildings, and we can only move to buildings which has a height greater than myself. So if you are standing at building 4, it can move to buildings which has a height greater than 4. So we can move to 8, 5, not 2, but we can move to 7. So this is how a person can move. And the query says that we have been given two indexes or two buildings where two people are standing, Alice and Bob. So first query says 0, which is 1, which is 6, and the first index, which is 4. So these two buildings need to, or these two people in these two buildings need to meet at building X, where uh, so if you see the next greater element, we need to find, we can see that we need to find something greater than 6 in order to, and greater than 6 and 4. Okay, and this building has to be right after 4, has to be after 4. So if you see, we have 8 which is right after 4, so this can be our building where we can meet. So we need to give the leftmost building. It has the question is asking which is the leftmost building where Alice and Bob can meet. So if you see, leftmost will be the first index after the second index, right? After this index. So we can see, we can see that we need to return the next greater element, okay, after the greater index. So between these two indexes which has been given to us, which is the greater index? 4, which is this index, which is index 1, right? And what is the greater element between the two of us, between the two of the indexes? Greater element is 6. So we need to find a greater height building which is after this index 1, right? So so these two conditions are followed by it, because this is greater than 6, because it is greater than 6, and it also comes after this index which is 4. So it comes after index 1. So we are returning the index of this building, which is 2. As we see, the height is 0th index, so this will be 2. If you see this one, this query, 0 and 3, right? So 0th index is again 6, and 3 is 5. 0, 1, 2, 3, yeah. So we need to find a greater height building than 6, because 6 and 5 we have. So we need to find greater than 6, right? We have to find greater than 6, which is after this index, right? So what we can see is, we see that after this index we have only 2 and 7. So 2 cannot be an option because it is less than both of them, and we can see that 7 can be our answer, because 7 comes after the second index, which is this one, max of the second indexes, and 7 is greater than the greater of the two buildings. So yeah, this, the index for 7 is 5, so we are returning 5. Now there can be scenario where no greater element exists, right? So if you see, for the particular query 2 and 4, right? So for 2 we have 8, and the fourth index will be 2. So we need to find something which is greater than 8 and comes after this index, right? And comes after this. So we have nothing which is greater than 8, because the only index, because the only element which we have after 2 is 7. So right, we will return -1 in that case. Yeah. So how can we solve this? What data structure algorithm comes into your mind? So we see that we need to find the next greater element, right? So for that we can come up with a heap, or rather minimum heap, to be precise. So we can take a minimum heap, but how do we implement that? we know that height can be, because we need to sort it on the basis of height, so height will be our key, and we'll be passing out and we'll be passing out the query index as our what to say, second parameter, in order to keep a track of the query, which query is it asking for, the greater element. And we will be taking another data structure where we'll be storing, because if you see closely, what is the query asking us? Query is asking us two things. For a particular query, we need to find greater element between these two indexes, right? So if we take one query at a time, if we take 0 and 1, so which is the greater of these two indexes? 6. So we will be needing 6, and we will be needing the index, right? Because we have 0, we have 1. So a greater element than 6 should come after index 1, right? It should come after index 1. So we will be storing nothing but a pair which will be storing the maximum of the two buildings, which is 6, and this will go in the index which is greater than the 2. So let's say we have this, right, 2 and 4, right? So if you see which is the greater of the two, 4, and for this also we have 4 greater than the 2. So if you see, uh, we have 8 and 2. So there can be more than one query, there can be more than one query which will require its greater element after that index. So if you see, for the fourth index, right, for the fourth index, which is this one, we need a greater element for two of the queries, right? So for the first query, the greater element should be after this after this fourth index, and the element should be greater than 8. And for this query, it should be after this fourth index, and it should be greater than 5. If you see, the third index is asking for nothing but 5, and we have in the fourth index 2. So this will be requiring us to give us a greater element after this index, and which is greater than 5. So let's code it up, and it will be much more clear to you, and we'll be able to understand on the fly much better. So we know that we will be needing, uh, so let's first store the heights, the size of the arrows, right? So we have heights dot size and query size. Right? So what do we need? We will be defining a container, right, where we'll be storing, where we will be storing a pair, add queries. So if you see, this will be storing nothing but a pair of maximum value of both the heights of the building and query index, that which index is it falling for, which is the required index between the two, right? That will be the case. And you will be asking that, okay, we need the greater of the two indexes, right? But what about the index that it should come after that? So that, for that reason, we have defined this pair of vector. So that is why I have defined it within a vector, right? Because for a particular index there can be multiple queries, right? If we see, for a particular index, if we see in this scenario, we have 2 and 4, we have 3 and 4. So for a particular index 4, right, we can have multiple queries. So there can be multiple pairs for a particular index. That is why I have defined it within a pair, within a vector of uh, pairs, right? So yeah, then we'll be needing a priority queue which implements minimum heap. So if we take pair of intent, because we know that the key of the priority queue will be the height, and the second one will be nothing but the query index, right? So since it is uh, minimum heap, we will be defining with the default comparator greater, because if you know, this greater returns or sorts it in the descending order, right? C plus plus. So we have our priority queue defined. Now we will be eliminating those queries which don't require us to calculate a next data element. Say in case there will be a query, if you see in the second example, we have 0 and 7, right? So if you take this query, we have 0th index, which has a building height of 5, and at the 7th index, which is 6, which is this is the 7 and 0, 1, 2, 3, 4, 5, 6, 7. Yeah. So 6 is the 7th index, and we have its height as 6. So if Alice is standing as at this building and Bob is standing at this building, Alice can come to this building and meet Bob, right? This can happen because the second index itself is greater than the first index. So the second index, so the first person can come to the second person in order to meet, right? So this can be one of the scenarios. Now what can be second? Second can be, this can be altered, like if we have been given 7 at first and then we have been given 0, then that will be the same scenario. Say Alice is standing at this and Bob is standing at the 0th index. That can also happen. So this is one of the cases. Now second case can be both of them are standing at the same building. If you see, okay, we don't have this case, but let's say both of them are standing at this. So here if you see, right, 2 and 2, so both of them are standing at the second index, um, which is 8 and 8. So both of them are itself meeting at the same index, so they don't need to travel anywhere, okay? And we will just return the same index. So we will be eliminating these scenarios and we'll be only filtering out those queries where we'll be requiring the next data element to be calculated for. So let's iterate through the query size. If we take query of I, it will be starting from 0 and it will go till the query size, right? And now for each of the indexes we have, for each of the queries we have two indexes, right? So we have index I, which will be giving us yeah, so for this, at index query of I, the first index will be giving us I, the first index will be giving us I, the second index will be giving us the J, right? Now if we see, there can be two possible scenarios or other three. Let's come to that. So if we have I is greater than J, right, and the height of heights I building is greater than heights of jth building, okay, then we see that I is coming after J and the height of I is greater than height of J, then I can be our index where J can come to. So we will just, okay, we are storing an answer, so for that we will just define another vector of our answer. So this will be giving us the indexes, list of indexes, so it will be a vector of int, and we'll be defining this will be of length size, right? And we'll be defining this as default -1, because if we don't find the next data element, or if we don't find an answer for the query, we'll be returning -1. Yeah. Now for this query index, right, we can just store I. Now similar to that, we can also do this the other way around. What if we have J greater than I? Then that will be the same thing. J is greater than I and the height of J is greater than the height of I. Then our answer can be the jth index. And what if I is equals to J? Then you don't need to go anywhere, right? You don't need to go anywhere. Either of the two cases will be our answer. If none of the above satisfy, if none of the above satisfy, then we will be needing to calculate our next weight element for the given query. So we will be, as you see, for the given index J, or whichever it is the greater between the two indexes, so whichever is the greater between the two indexes, will be at that index will be pushing this pair, right? We will be pushing the maximum value between the two index heights, and we will be pushing the square index. So if you understand that clearly, we will be pushing um, in the required query maximum between, we'll be pushing at the maximum index between the two of the indexes given to us in the query, and we'll be pushing back a pair where we have max, okay, where we'll be having maximum between heights of I and heights of j, right? Yeah. And in the second we will be pushing the index which is query of I. So this will be uh, giving us the all the pairs for which we need to calculate the uh, next grid element, right? So at now we will be calculating and we'll be operating for these of the indexes, these of the queries which we have. So we are pushing it at the jth index, right? So at max the indexes, the index j can be up to n length because we are pushing out the indexes for this query. So for at max the query can be of length j, right? Because the index can lie between 0 to n minus 1. So we'll be going across that, and we'll be checking whether the priority queue is empty or not. If it isn't empty, that means we have a query listed between we have a query inside the priority queue, and we will be taking the top element. We will be taking the top element. So the top element we will be taking this pair, right? So this should be greater. So we will be needing something greater than this. So if we have first, which is the maximum value height, which is the max height, if we have something greater than this, right? We have something greater than this. So if the height of I is greater than the top element, then what we'll do is we have got an answer. Then we can store an answer of in this index, right? Because in this query index we can store the particular index of I, because this index is greater than the top element. So we can push that. So it will be coming as pq dot top second is equals to nothing but heights. Okay, we'll be pushing the index, not the height. So we have pushed that, and we can pop this, right? And pop this. Otherwise, for the particular index I, as we know, for a particular index I, we can push all the required queries which we had, all the required queries, the pair of queries which we had. So we'll push that query of required query. We'll pushing this the queue, right? So eventually this will pop us our answers. And for the element which will have nothing greater, so for that for those elements, okay, say for 8 we didn't have anything, so for that the query doesn't like this thing doesn't gets populated, and we'll still have that in our priority queue. If you go and iterate through and do a dry run with this code, you'll see that this element 8 for the query 2 and 4, it still remains in the priority queue. We don't operate on that, and for that index we have by default stored as -1. So that will handle our case. So if we return, our answer should get done pretty much. Okay, there's a typo. Yeah, let's see. pq dot push. What do we have over here? Right. So the for this index, right, for the particular index of I, we will be pushing this. Right. So yeah, be careful with these things. We have another mistake under offset. right? We need to define this query with the size of n, right? Because we are pushing it, right? So when we are pushing it, we should be having this as defined. So that needs to be defined. Yeah, we have this ready. Yeah, thank you guys. See you in the next one. Please don't forget to drop a like and subscribe.